We're going to start back up with chatter diagnosis and milling using supervised learning and topological features vector. And this is Sarah
Tymochko, yeah. All right, hi everyone. Thank you so much for coming to the second session here. So I'm Sarah Tymochko. I'm actually presenting this on behalf of my co-author who led this project, Melih, who unfortunately couldn't be here to give this talk himself. But this is work that was really spearheaded by him and then helped out by me, Dr. Firas, Khasawneh, and Dr. Elizabeth Munch. So the goal of this project is to diagnose chatter in milling, which, so the setting of this problem is if you have, in mechanical engineering or engineering practices, you have some sort of workpiece that you're trying to cut, and you have the cutting tool that you're sort of rotating along the metal that you're trying to cut to make a clean cut across the workpiece. And so there's two different ways of doing this. So one of them is called upmilling, where you're moving the piece that you're trying to cut along the top of this sort of spinning blade thing. Sorry in advance, I'm not a mechanical engineer, so apologies for the not technical terminology here. But so you have the workpiece that you're sliding along the top, and it's sort of going opposite the direction of rotation of the cutting tool. The other way of doing this is down milling, where the piece is below, and you're sort of cutting in the same direction as the workpiece is moving. So this will give you two different results. So there's a lot of issues when it comes to this cutting, because you can end up with different stable and unstable behaviors here. So maybe you're getting that the workpiece is sliding nicely along the cutting tool and you're getting a nice clean cut in the stable case, but you can also get the unstable case where you're sort of bouncing around the ridges that you might want to be smoothing out. So that can cause a lot of issues in the piece that you're cutting itself, but it also damages the work tool that you're using, so it would reduce the lifespan of this piece that's cutting as well. So it's an issue of both ends of the process being damaged along the way. So it's an issue that can be, so this is an example of it shown on the actual piece that was cut. So you can see on the left you have a nice smooth surface there. So that would be the stable case where you're sliding along nice and clean. But on the right hand you can see that sort of jagged behavior there, and that you definitely would not want for a nice smooth piece. So there's ways of detecting when you would get this sort of behavior in theory. So this is sort of a bifurcation diagram of where you're going to get stable and unstable behavior based on the rotation speed of your cutting tool, as well as the cutting depth that you're using along the vertical there. But you can see it's very jagged and sort of uneven, so you can very easily cross this in practice when it might not work as nicely as in theory. So our objective here was to use topological feature vectors to diagnose when this chattering is occurring and when we're getting the nice smooth behavior that we want. So the general outline of this talk is going to go through the pipeline that we use. The data that we're using in this case is actually simulations of this milling process, so it's not real data recorded from the machine, it's just a simulation. A brief introduction to TDA and a couple of the featurization methods we use, as well as the results in practice. So the general pipeline works similar to a lot of what we've seen so far. So we have some sort of data that's been normalized nicely. And the difference is we have time series data here. So what we're going to do is something called Tokens embedding, which is just a way of taking a time series and embedding it in a higher dimensional Euclidean space. So now rather than a time series, you have a point cloud representation of that time series. Then we compute the persistence diagram on this point cloud using our standard RIPS filtrations. We extract the topological features. In this case, we're going to use crossing coordinates and template functions, which we just heard about from Luis. And we're going to use standard machine learning classification methods like SVM, logistic regression, random forests, and gradient boosting to see how all of these perform in practice. So the way that we're going to model this is using this equation here. So there are a bunch of different parameters that go into the model. The right is the forcing function. So this describes our equation of motion of the cutting tool on the surface. And the cutting force here that we're using is going to depend on the current time as well as a little bit prior to that, because that can affect moving forward how the force of the tool is working. And so then we can convert that to a state space form where the details of this are given in the reference at the bottom of the slide there. But this is just a way of modeling the behavior without actually using any of the tools or damaging any of the cutting pieces or work pieces that may be damaged in this sort of process. So the way that these simulations were done was given this sort of bifurcation diagram. Here we have 3 different classes. So we have the stable case, and then we have 2 different cases where we're going to get instabilities. So that's the Hopf case and the period doubling case. And so for both the down milling is on the left and up milling is on the right, we're going to take a 100 by 100 mesh on this bifurcation diagram and take each one of those parameters into our model and compute an example for that. So each one of those colors is actually a little point there, and each one of those points is going to represent a time series. So we have a huge amount of data here sampled across a whole variety of these different parameter options. And we're using both the down milling and up milling cases to see how they vary across it. So I don't think my animation is going to work here, but hopefully we all have a general intuition of persistent homology, where we have some sort of point cloud data. We're going to expand disks around it using our standard RIPS filtration, and a strong off-diagonal point is going to represent that circular behavior. And so the more periodic that our time series is, the sort of better our circle is going to form, and the more we're going to see an off-diagonal point. So that's sort of the intuition for using persistence in this time series case. So the first featurization method we're going to use are what are called these Carlson coordinates. So it's these 5 different evaluations on the coordinates of the persistence diagram. So we're looking at, for example, the first one is multiplying the birth time times the difference between the death and lifetime. We have all these different varieties. So we're going to evaluate each of those on each persistence diagram, and that gives us 5 numbers for each persistence diagram. So that would be one feature. And then if we have multiple different dimensions of diagrams, we would do this on each dimension separately and concatenate those vectors together. The next method we're going to use is these template functions. So we're going to use interpolating polynomials on persistence diagrams to create this vectorization, similar to what Louise talked about earlier. And so we're going to define our persistence diagrams in birth lifetime coordinates. So rather than having death on that y-axis, it's just going to be death minus birth to make things a little bit nicer. And the template functions here are defined by just evaluating that function on each point in the diagram and summing it up. So for each function on each diagram, we get 1 number. Then we take a collection of these functions, do this repeated times, and this gives us a featured vector for that persistence diagram. So the template function that we're going to use here is the interpolating polynomials. This is an example of the one-dimensional case here. So the interpolating polynomial is this product of this fraction, but basically what it does is the jth function evaluates to 1 on that jth point in the mesh and evaluates to 0 otherwise, and then the rest of it interpolates nicely in between. And so then when we have 2 dimensions, we just multiply the product of these, and you can see the plots on the bottom right here show this interpolating polynomial. So the entry, where the entry is located is going to tell us which point we're sort of centering this interpolating polynomial on. So this one is centered on 2, 2, 1, 1, 1, 2, and so on. So you can see how this sort of changes depending on where we're centering the function. And also in our formulation, we have to include that beta function because we need our template functions to be compactly supported. So that beta function is just going to be a bump function to sort of restrict to where we want it to be located. So the first results here, this is using the 2-class classification, so just whether or not we're experiencing chatter or not, or stable versus unstable, and this is the down milling case. And here, so this blue and red line here represent 0-dimensional diagrams using both of the featurization methods that I mentioned. And you can see that the results are not so good. So going across the y-axis here are different levels of noise. So on the left, there's absolutely no noise added to the model, and then the further right we move, the more noise is added. So you can see that as we add more noise, the 0-dimensional classification just degrades very quickly. So we ended up deciding to leave that out of the rest of our analysis because it didn't seem to be providing as much information as using 1- and 2-dimensional diagrams. So here are the results. Sorry, they're a little bit difficult to see on the projector here, but on the left we have the results for the 2-class classification problem. The top is the down milling, and top is down milling, bottom is up milling, which is a little counterintuitive. Sorry about that. But you can see that as we increase the noise, something sort of also counterintuitive happens, where when we have no noise, we're getting pretty good classification rates, but as we increase the noise, we're getting worse, and then we're getting better, which is a little bit strange and went against our intuition of what should be happening. And on the right is the 3-class classification problem, where you can sort of see the same patterns, but since we have 3 classes, the results get a little bit worse. Then these plots here are plots of those bifurcation diagrams, where the blue points are going to represent where we successfully classified what was going on, and the red is where we incorrectly classified what was going on, whether it was stable or unstable. And so you can start, it's pretty hard to see, but at least in the upwelling case, a lot of these incorrect classifications fall sort of along that bifurcation line here and here. So it's sort of where we would expect to see bad results, because that's where you're crossing from a case where you would expect no chatter to chatter, so maybe that line isn't so clear in our classification. Up here it's a little bit noisier, but there are definitely some that also fall on those lines. So the other thing we tested was how many, they're called teeth on this cutting tool we're using. So in that figure across the top, either we have 3 teeth coming out of our cutting tool, 4 or 5, and that can also change the behavior that you're getting when you're doing this cutting process. And so again, we're sort of seeing that unusual behavior where as noise increases, we are getting some sort of increase in accuracy at the end. But across all of the different, the bottom is 3 classes and the top is 2 classes, and the number of teeth is increasing across. But we are getting pretty good accuracies. The numbers here aren't super clear, but I think this is around 90% maybe. So we're getting pretty good results classifying these different things using the topological methods here. The little bit of intuition that we have as to why this noise thing might be happening is because persistence, we know, is very robust when it comes to noise. So maybe the noise isn't actually contributing as much as we think, and it has something to do with the simulations more than how much noise is being introduced, because persistence is so robust, maybe that isn't changing as much as we think, and there's some other underlying factor that's going on. But for a lot of cases here, it is clear that the persistence-based methods are able to classify this chatter behavior pretty nicely, which could be helpful in real life when you're trying to do this cutting, not on a simulated case, because you could use this sort of to determine when you should stop or when you should adjust your parameter choices. So acknowledgements. Mainly I need to thank Melih, who was an awesome lead author on this project and did so much work that went into this, and unfortunately he couldn't be here. And also our collaborators, Dr. Khasawneh and Dr. Munch. His email is up there, so if you have any questions for him, please feel free to contact him, but I'll take any questions now. Thank you.
Okay, we have some time for some questions. Anyone want to start off?
Yeah, thank you for the talk. I have a question, is your approach also viable? Can you model the condition of the cutting tool? If it degrades and you get some weird phenomena happening, so then the forces change and stuff. Can you model that with this approach?
So that was not taken into account in our model here. It was just ideal cases, what would happen if everything went nicely, So the issue of the wear and tear, I think, was not taken into account in the model. Yeah. So
this phenomena that you noticed with adding a little bit of noise, increasing the classification accuracy. So I've observed something similar happening before. Maybe what's happening is by adding a little bit of noise, you're closing the gap in the small features near y equals x in the persistence diagram. And so it's sort of smoothing over those small things in H1 that are, they're getting filled in faster, so they persist less, and all you're left with are the larger parts. But
yeah, that makes a lot of sense.
Just intuitively, it seems to make a little bit of sense.
It does, yeah. The idea that it would get better with noise is counterintuitive, but what you said definitely makes sense as to why that might happen in persistence. Thank you.
Just a follow-up to that. What type of noise did you say?
So it's, I think, just normally distributed noise, if I remember correctly, across the time series itself. I don't remember the exact details of that.
Okay, I think we have time for one more question.
Yeah, like I'm curious about, like you said, you have like time series variable, and like you're having the cutting force, or what like variable are you observing? It's the cutting force, or like
yeah.
did you also like just look at the cutting force, or also other forces? Because I'm curious about that.
Yeah, no. So actually, I don't think it's the cutting force. What we looked at was the velocity of the piece as it's moving across.
Ah, okay.
Yeah.
Okay, if you have any other questions, maybe take them up later after the session. Let's thank our speaker.